Oh, here you are.
Oh. Okay.
Please just stay like that, right? Excellent connection.
Okay, it looks like it's.
Yeah.
And
Okay.
how's the?
No, the banner.
Could you please fix that?
No sound as yet.
Sounds good.
No sound.
No sound.
Cool.
Hello?
I'm getting talking. It's a bit quiet.
It's a bit quiet. Hello.
It's about a 30-second delay, so I'll hear that in 30 seconds.
It's alright. I
Make
think
it a bit louder.
If I yell, it's because that sound comes through very badly.
Are you also one of them?
Sorry?
Are you to study?
What did you say? Sorry?
And are you also one of them? Like, are you going to teach?
No, I'm not smart.
no, everyone's smart enough for this.
You're doing like
Everyone's smart enough to teach stats.
That's not a jab against stats people, is it? William, do you know if it's?
Still sound a bit quiet.
Should I? Hold on.
I mean, OBS is as high as it goes, right? So.
It is, isn't it? It should be fine, but I don't know why it's
Isn't the
not.
holder really close to?
No, yeah, but that's
elbow
not, that's not
cords?
right. It should be. What? What happened? No.
The stream is still up. So it's fine. It's just frozen, right?
It's a bit quiet. I don't know.
What do you?
It is fine. It's a bit quiet.
Oh, here you are. Oh. Yeah, yeah.
It's alright. Because I've only got 7 questions.
Yeah.
I mean. Okay.
Yeah, I think we're good to go.
That works.
Guys, will you all be teaching like MATLAB as well, associated with it?
I'll be going through some of the commands, but yeah, I won't be able to get it up like side by side just because of the streaming. But yeah, I'll be going through all the MATLAB commands basically you'll need to know.
Thank you.
Yeah, there's really not that much. Yeah, the stats part for the majority of it is just kind of the formula booklet. Like it's a formula sheet you can use. It's only the last little bit with standard error, and that you need to actually do.
I just heard everyone's smart enough to
Okay.
teach that, so that is loud enough.
It is? Okay, that's good. I think we'll just get started now.
Yeah.
Okay, actually, I'll just hold it. All right. Hi, everyone, in person and online. Thank you all for coming. A bit of a slow start. We had a bit of technical difficulties, but we should be all right now. Okay, so welcome to the Math2B midterm crash course. Hopefully you guys find content we go through today useful for your preparation for the stats midterm next week, and then the linear algebra one the week after that. So before we get started, if you could please scan that QR code for attendance. It helps support ELSOC. We get funding for this, and it's just good to sort of keep tabs about sort of engagement with our academic material. Ooh, it says someone's got frequent freezes. Okay, let's have a look. Sorry, I'll try to fix that, Joshua. Okay. okay. We'll see
Should we set a
if someone else
score?
asks
Yeah.
something, and then maybe we'll.
Yeah, I
go
think
after
it
that.
might be
Okay.
a Jerome.
Potentially.
Yeah.
Okay, I guess we'll just get started then. All right, so we'll start off. So the structure of this crash course we'll begin with stats for maybe the first half, and then we'll move on to linear algebra afterwards. And yeah, so Sid will be doing the stats part of the crash course. You are Sid.
Thank you, Leith. So, yeah, for stats, we'll be going through lectures from 1 to 5. Although I do acknowledge that most of the midterm will be focusing on lecture 3 to 5, so we'll kind of just talk very briefly through the content of 1 and 2. So we started out statistics by actually asking what it actually is. So very straightforward. We collect data from experiments and we try to extrapolate it. We try to infer things about things. You know, there's 27 million Australians. If we only take 1,000 of them, what can we infer? Is that very fair? Yeah, we draw conclusions, and mainly there are two types of branches for statistics: descriptive and and yeah, it's just basically, well, we're not really going to deal with categorical data as much in the midterm. But yeah, here are the 4 types of charts that was covered: bar charts, histograms, box plots, and scatter plots. Bar charts are used for categorical, histograms are for distribution. And the main difference is histograms, they don't have the gap between each of the bars, they're all together, so it really shows that relation. And yeah, a box plot shows the quartiles, and yeah, a scatter plot visualizes between 2 quantitative variables, which is the one we normally use in any science experiments to show trend. Now here are our key formulas or terms. So our mean, which is just also sometimes referred to as the expected value. So in a very simple term, yeah, what's the most what's the average of the data set? That's what the mean is. And most of the time you'll be using MATLAB to find it. Mean, group X. Variance. Because if we kind of consider what variance is, it's very, it's kind of conjured up, right? Like, because the difference between every single other data point from the average would always equal to 0. So we kind of need to find the absolute difference, which is this variance here. And we get the absolute by squaring it. But, you know, to get the actual deviation, we then square root the variance to get standard deviation. So once again, most of the time you won't need to calculate this. You will just need to use the varx and stdx on MATLAB. The interquartile range is Q3, which is the median of the upper half of the data, minus Q1, the median of the lower half of the data. And that gives you the interquartile range. Once again, IQR in MATLAB. And yeah, the outlier rule in general is just 1.5 of IQR above or below the 3rd quartile or the 1st quartile. Yeah, and anything below or above that we say is an outlier. So here's a very simple question. We have 5 exam scores: 70, 85, 90, another 75, and an 80. Find the mean. Add them all up, divided by 5, you get 80. Yeah, for the different, for the variance and standard deviation, you can do it this way, although I wouldn't. Just put it into MATLAB. So that format would be x is equal to square bracket and then all the data set, and then you can just work on x from that. Okay, very straightforward for lecture 1. Lecture 2, now we need to talk about something called random variable. Yeah, so it's basically when numerical outcomes are random, are randomized, and that is a very important concept to everything else we do. We need to make sure that everything we work through are not influenced by each other, otherwise we can't actually continue to do any of the mathematics. Yeah, and the 2 most important functions here are PMF for discrete distributions and PDF for continuous. That finds the probability of a single event for any distribution. So probability distribution function is PDF. And then next up is CDF, the cumulative distribution function. And what both of them do is, if we imagine for a discrete distribution, the PMF measures what's the likelihood of, let's say, the second event from happening. That is that specific event. And the cumulative, which applies for a continuous case, we ask for a point, and what's the chance of it happening before this point here? Let's just call that A. And as we go through each of the distributions later, all we have to do is add these functions behind them. So if it's binomial distribution, you just need to do bino CDF, and then follow whatever the structure it is needed. Yeah, okay. So here we have how we calculate some of our expected value. So for the mean, it's the sum of the event itself, if it's discrete, the event itself times the probability of it happening. So for a dice is 1 on 6 times 1, 2, 3, 4, 5, 6. Add it all up. And if it's a continuous function, it's actually this integral here. The integral of x multiplied by the function of x, or it's the position at which the integral is equal to 0.5, exactly where half of the integral is. Because for any statistics, the area under the curve will always be 1. Yeah, once again, you can do this if you want, but mean is very important. Okay, next up for variance. This is a very important formula, actually, for just having a look at some of the practice exams, because sometimes they'll actually ask you for the expected value of an event squared. Now, that might seem very weird, because if let's say, the average of an event occurring in a week is 3, and I ask you what's the likelihood of that event occurring in week squared, you might just say 3 squared, 9. But no, it isn't. Those are two completely different things. And how we can find this event of x squared is by using this relationship between variance and the event itself squared. Yeah, so using this, we can just rearrange of x squared is going to equal to the variance of x plus its mean squared. So sometimes this can be popped up on the first question on the practice test. Just be careful with that. Yeah, and most of the time the variance would be given to you, or standard deviation would be given to you, and you can square that to find variance. If not, yeah, MATLAB is your friend. Next up, we come to this idea of standardization, which is a z-score. Now, all a z-score is, in theory, is just how many standard deviations is this value from the mean. So if you have let's just go with the standard normal, right? Which is mean at 0, standard deviation at 1. If it's got a z-score of 2, it means this value are 2 standard deviations away from 0. So it's got a z-score of 2. And we can use this logic very usefully when we get to lecture 3, 4, and 5 to utilize it to transform any normal distribution to a normal distribution, the standard normal of mean 0, standard deviation 1, to help, just use z-scores to obtain information. Next up, covariance and correlation. I have not yet come across any questions that involve these, And even if they do MATLAB, you'll be using MATLAB anyway, but it's a measure of how two different sets of data might be related to each other. So the covariance gives you a range, like an output that's pretty much any real number. If it's positive, it means the variables increase together. Negative means as one increases, the other decrease, and 0 means there's hardly any relationship. It's completely randomized. And yeah, if you ever need to use or calculate covariance, just use MATLAB, cov x and y being the two sets of data. Next up is correlation, very similar to covariance, except it gives you a range from -1 to 1 instead. Pardon me. If it's -1, it's very negatively correlated. As negative, like it's a straight up negative correlation. If it's 1, it's extremely positive correlated. If 0, not at all. Yeah. Once again, if ever needed, MATLAB. It's CoRR, X, and Y. Okie dokie. Now we reach some of our distributions, and this is where things start to get really important. So we start out with our binomial distribution. This is a fundamental one for discrete distributions. So flipping a coin, or a chance of something failing in production. It's a chance of someone doing a double degree. If it's a yes or a no, chances are it's going to be binomial. And we can find the... okay, so mathematically we find the chance an event is going to occur using this formula here, where P is the probability of it occurring. So if it's 5%, it will be 0.05. N is the number of is the number of events that is going to occur, and K is the total number of events. So for example, what is the chances of one coin flip out of 4 being a head? So N in this case would be 4, K is 1. And this function here is just a combination symbol. So 4 choose 1, and then P to the power of K, 1 minus P, N minus K. You could do it mathematically, or you could just use MATLAB. So in this case, we would do bino, PMF, and then I think the order is KNP. It will tell you when you just enter bino PMF open bracket what the next 3 variables should be. Which is why I haven't really gone to the effort of remembering it. The mean in this case is the number of trials multiplied by a percentage of that trial occurring. So 4 coin tosses, that's 4 trials, chance of being head is 0.5. So on average, you're going to get 2 heads. And variance is just this mean multiplied by 1 minus the chance of happening. Yeah, okay. Ignore this R&D, that's pretty useless. Instead, remember CDF instead, cumulative distribution function. That is when, let's say you actually have something, for example, a production of pencils, and potentially 1 out of 50 could fail. The chances of zero, 1, or 2 out of the pencils failing, if we want to know the chances of those 3 options, we can do CDF up until 2, and that gives you the cumulative property. So it counts 0 plus 1 plus 2. You can do it the other way around. You can say, what are the chances of it not failing? So from 0 all the way up to 45 successful trials, or vice versa. So in that case, when you're calculating the chance of more than just one outcome, CDF is the way to go, cumulative distribution function. Next up, Poisson distribution. It is very, very similar to binomial in the sense that it is still discrete, yes or no, 1 or 0. But in this case, we are modeling the event of something happening in a fixed interval, in a fixed time. What are the chances of this event happening more than twice in a week? And you will be given a fixed interval with a rate, in this case, lambda here. And the very useful information here is lambda, it will always be equal to both the mean and the variance in a Poisson distribution. And yeah, here's the formula. If you're really interested, it's on the formula sheet. If you want to do it by hand, I wouldn't. Use MATLAB. It makes your life so much easier. Poisson PDF, K, lambda here. Yeah. Obviously, K being the number of trials. Okay, here's where we start to get into our continuous distributions. We start with our exponential. It's basically, yeah, when an event has an exponential chance of occurring along with time, potentially skin cancer with age or something. Yeah, here is a formula. You will be given a lambda, and X is your likelihood of the event. The mean, 1 on lambda, variance, 1 on lambda squared. All these formulas are in your formula sheet, but please, please, please just, for yourself, if it's just the mean or variance, that's fine. But if you actually want to get the probability of something or the probability of between two ranges, do not calculate it by hand. Always use MATLAB. Very similarly, EXP for exponential, and then PDF for just the one event, and then CDF for cumulative. It'll make your life so much easier. Yeah. We'll talk about normal in the next slide, but also something else that might occur is a uniform distribution. So basically, the likelihood of something is constant through a range. Yeah, I'm not going to spend too much time talking about it. If they ask you a question about it, just remember it's always going to be equal. So the error under the curve will always be 1, just the error of a rectangle. And yeah, if you need to find the standard deviation or mean, you can always use MATLAB for it. Here we have a sample question. Yeah, so a factory produces a light bulb with a defect rate of 2%. What is the probability that exactly 3 of 10 bulbs are defective? So, using our formula, 100 choose 3, multiplied by the chance, p, 0.02, to the square, to the power of the event, 3, and then 1 minus the probability to the power of n minus p. Or, alternatively, using MATLAB, Bino PDF, 3, 100, 0.02. So, N, K, P is the order. Okay. Any questions about any of the distributions in the room so far? All good? Perfect. Next up, standard distribution and central limit theorem. This is the most important bit for the midterm and perhaps the most tricky. The normal distribution is basically a symmetric and bell-shaped curve. We've been drawing this for a very long time. And remember, the integral, the area under the curve will always be 1, no matter what it is. And this includes the normal distribution. And the formula is given through this very long thing. I don't think you'll ever need to get the formula because you don't actually need to like draw it out at any point. But yeah, it's as long as you conceptually understand that it's a bell-shaped curve, and yeah, it's this idea that it's got a standard normal then, and we can transform any distribution that is normal to a standard normal we'll talk about later. And using z-scores, which is how many standard deviations something is from something, from the mean, sorry, we can work out a lot regarding the distribution. And the three main functions in MATLAB we use are norm PDF, norm CDF, and norm INV. In fact, norm PDF, very, very limited usage just because it's a continuous function. CDF would be the one you're using most of the time. So if we imagine, if we're trying to find the range, the probability of this section, we would first use CDF to find this entire thing, and then we would subtract the cumulative distribution of the yellow to find just the red section. And norm inv goes the other way. It's given a known z-score, what is the cumulative distribution under it? So given, I think, 0.975, you can use norm inv, you can use norm inv 1.95, and it'll give you 1.975, I believe, as a z-score. But yeah, it's going the other way. If you have a z-score, what's the probability of it? If you have a z-score, what's the distribution of it underneath? Sorry, that's 0.975. Okay, and now central limit theorem. It's very key, and it allows us to infer information from a very small sample and project it onto a much larger sample size. So it's for a very large n, the sampling distribution of the mean approaches normally. And the sample itself doesn't need to be normally distributed, but the mean of the sample that we collect will always be. So if you're given a trial, for example, and it's said we've collected 15 different normals, here is set X, how can we use it to infer things? You can always say, well, these 15 means will be distributed normally, and we can use a normal distribution to go on with greater things. Okay, and here is the sample size effect on the mean and the standard deviation. So when we have the mean of a larger population, for example, 1,000, if you take just 100 randomly, by the way, this all has to be done randomly, what is the mean and standard deviation of that smaller sample going to look like? Now, if we imagine randomly choosing 100 out of 1,000, the mean would probably be the same, if not around the same. So the sample mean would be the same as the wider population, but the standard deviation would be different. Because smaller samples are more variable, there's a higher chance of you selecting something that is having a greater difference to the mean. And because standard deviation is the square root of variance, and variance is the one being directly affected, the formula we need to remember here is that the standard error, so in this case, you can imagine standard deviation of the smaller population would be the standard deviation of the entire sample size divided by the square root of n. And you can find that on your formula booklet, not directly, but it will be on the standard normal. So if you have a question that asks you, what's the standard error of this smaller population that's being collected, use this formula to find it, given you have the standard deviation of the entire population. Okay. Next up is the effect on mean and variance and standard deviation when it's subjected to linear transformations. And this will be useful, sort of later on when we discuss estimators. But the effect on the mean, as you can imagine, actually that should be plus b. It doesn't really matter how many times we multiply. The effect by the standard deviation. Okay, for most parts, just to answer a question on YouTube, this is just year 12 revision. Very, very true. Apart from the use of MATLAB, I don't think you use MATLAB in year 12. Okay. Here's an example. The height of a student are normally distributed with mean 170 centimeters and a standard deviation of 10 centimeters. What's the probability of a student being taller than 185 centimeters? So first we can find out the Z-score of 185. How many standard deviations do you need to be from the mean to be above 185 centimeters? And thus the answer. Alternatively, you can use MATLAB to find the cumulative distribution, which is going the other way of finding what is this entire area. So you're giving it the x of 185, the mean of 170, and the standard deviation. It'll figure out what this area would be, and 1 minus that would also give you the answer. Okie dokie. Okay, if we're increasing it from 100 or 200, 300, 400, and it's not getting closer, then it's not consistent. Actually, this doesn't just apply to the mean, it applies to the variance as well. So if the variance is not approaching the variance of the larger sample, we cannot call it consistent as well. Even if the variance is getting extremely small and we're getting extremely confident, it's not consistent. Okay, and lastly, we have whether it is efficient. So, yeah, it's just... Okay, so first let's talk about the standard normal here, which is this formula I've just quickly written. This is just, if we have a look, the only difference here and the formula for the Z-score is that we have substituted in our standard error here instead of just the standard distribution. And what that does is and standard deviation 1 by subtracting it by the mean and dividing it by our standard normal. So everything here. So now we can go the other way around. So given we're trying to find the error between two Z-scores of, let's say, negative 1.95 and 1.95, we can multiply it over. Okay, let's u smaller than x plus z. So now here we have constructed our confidence interval. And what we can imagine, how we can sort of intuitively understand this formula is how many Z-scores away, how many standard deviations away are we from our value to the mean. So, and then we plus or minus the sample mean that we got to find the confidence level. So if we want a confidence level, like for example here of 95%, yeah, we go from our sample mean and we minus 1.95 of our standard error for the lower bound and we multiply it for the upper bound. Oh, sorry, we add it for the upper bound. Now the key distinction here, and perhaps that is going to interfere with how we're going to do the mathematics. There are two ways. Just to kind of go through the main difference here. Instead of having sigma, we are now looking at large S, which is the standard error of our population, which is the standard deviation of the population we have collected. The sample size, of the sample size, basically. And instead of using the z-score, we are using the t-value instead. And the reason why it's t-value of n-1 is because we have n-1 bits of useful information, because the mean really can't, it doesn't contribute anything to our t-value here. It doesn't, so there are two ways we can solve. Open bracket h, comma, p, comma, ci, close bracket is equal to t-test. X is going to be your sample. Y, just type 0 because in this case, we're not comparing to anything. If you are comparing one data set to another, you will need to type another one. In this case, nothing. Name, in this case, we would say, so remember to plug in alpha for the t-test and alpha on 2 for your known standard deviation tests. Okay? Any questions about this segment? Any questions about the MATLABs? Good. Okay. And lastly, how can we use the sample proportion involved in these questions? Pardon me. So we'll sample proportion to just be the sample proportion of our data we've collected there, because we can't infer any more. The standard deviation we have is this: the square root of p, the sample proportion, multiplied by 1 minus p, or on n. You don't strictly need to remember this either, because the formula you are given in the formula booklet, keen-eyed folk might have realized that the formula given down the bottom here is not using p hat, is using pi. Now, it turns out that this expression is exactly equal to p, 1 minus p, over n. So this makes finding pi much easier once we substitute that in. Okay. And once again, we can use the exact same logic as this is also, because of a central limit theorem, approximately normal. Or, 0.95 for consistency. How many trials, how many data points do we need to collect to have a confidence interval of 0.95? We use this formula. It's a rearranging of our confidence, of our margin of error. Okay? Sometimes we using 0.5, that's the formula. Okay. And when we're using normal approximation for the binomial, we need to make sure that both the mean and the variance are sufficiently large for the binomial. Otherwise, it's a little bit dubious. So the rule of thumb that we've learned is the mean multiplied, well, not really the mean. So n multiplied by p multiplied by 1 minus p needs to be larger than 5. If it's not larger than 5, then we cannot be certain of our normal distribution or approximation here. Ci is equal to t-test, x, 0. Yeah, that's fine. X, 0, alpha in quotation. And our confidence interval here of 0 product, find a 95% confidence interval for the true proportion. So our sample proportion here, 48 out of 100, frankly. You know, surprisingly, it's 0.48, n of 100, and z-score of 1.96. Standard error, remember, is the square root of n multiplied by 1 minus n, all on, p multiplied by 1 minus p, all on n, which gives us the standard error. And it's just our mean, plus or minus z-score multiplied by standard error again to find our confidence interval. And the other way around, have a specific function you want to know more about, just type it online, TT test, you know, MATLAB. All the syntax will be online, all the approaches, there are plenty of examples. Okie dokie. Yeah, and lastly, we need to check for our rule of thumb. Multiply it, it's like 534, I think.
Now for the hard part of the course. No, should be all right. Okay, let's see here. Yep. All right. Can you guys hear me well? I'll take that as a yes. All right. So, in the course, we start off with chapter 1, which is sort of introducing you to matrices again. A lot of this is a rehash of first year maths, first year linear algebra. A lot of it is to do with Gaussian elimination. I assume that all of you guys are pretty comfortable with Gaussian elimination, sort of like matrix algebra, kind of difficult. So if I have, let's just say, the matrices A, B, this is not necessarily equal to BA. And that makes things annoying. You'd have to left multiply by certain matrices if you want to do the multiplicative inverse, if you want to get rid of matrices. So it isn't very friendly in that regard. Other than that, we've got a lot of other identities here. This is the zero matrix. So this depends on your dimension. The zero matrix is a square matrix, so it would be n by n, where if we had, let's just say, let n equal 1, so 1's a bad example, 2. 2 by 2, it would be 0, 0, 0, 0, A, B, C, D. Then the transpose of this matrix would be sort of flipping the matrix so that every column, let's say the ith column, becomes the ith row. And the jth row becomes the jth column. So if I had A, B, C, D, probably easier to illustrate, this would be equal to, let me just read this, would be I'm flipping the columns and the rows. So what I would get is that I would get A, B, C, D, E, F. Is this correct? Yep, that looks about right. And you can also see that this changes the dimension of the matrix. So this was a 2 by 3, and this becomes a 3 by 2 matrix. All right. You can also sort of see that if I take the transpose of a matrix and I take the transpose of it again, of that same matrix, you get back the original one. It's sort of like a bijection. It's 1 to 1 and onto. So in that way, it's sort of like, how long will this crash course run?
I can just answer that in chat because they obviously lag.
They are lagging, aren't they? Yeah. Well, I didn't actually, I need to check my, should have checked my internet connection. I am on EduRealm. Let's try Uniwide.
So you must still work.
I have no idea. Imagine this makes things so much quicker. Okay. And then if I just try, let's have a look. -1, -2, sure. then what I could do is that I know that v1 is equal to minus v2. And then I know that for values that are not lambda 1 so if I set lambda is equal to 1 and lambda is equal to 1 as well in this case, because I can do v1 plus v2 is equal to 0. Here the lambdas are 1. Well, then these are linearly dependent. When it comes to higher dimensions, it's not as clear, but it should still be sort of understandable. For 3D, what would this mean? If you have 3 vectors, right? If I have 3 vectors that lie on the same plane, then we say that they are linearly dependent. And the reason for that is that you can represent at least one of these vectors as a scalar, as the linear combination of the other 2. So this one could be made up using these 2, for example. Now, how do I get 3 vectors that are linearly independent in R3? Well, if I wanted to do that, then they can't be on the same plane, so they have to span all of space. So if I drew like sort of like a Cartesian, let me just draw the space. So this, let's just say this is x, y, z. Then this would be here, this would be there, and this might be, but I don't want to use that one. Say t of x is equal to, let's just say, x2 plus x3, x1. Let's say this transformation, right? This can be represented by some sort of matrix. So what I can do is that, well, I can actually just read off the matrix right here. What you would get is x1, x2, x3. You would have 0, 1, 1, and then you would have 1, 0, 0, I think. Oh no, hold on. Yep, I think that should be right. So what you can get is that you get a matrix of this form, and so this matrix sort of encodes this transformation. So you can do this transformation by multiplying any vector x by a, and then it does effectively the same thing. I have a definition here for linear maps. So what we say is that the image, or you want to find the transformed version of them, right? And that's all the possible values that this transformation can hit, right? So you put in every single x that you can do, and then you have a look at what vectors can you get on the output side that are possible or reachable. So that's the range. That's the image. There's other words for these. So the kernel is also called the null space. The image is called, you can also call it the column space. The column space, the name for this actually comes from the idea of like linear independence. So if you span the vectors that make up the columns of a matrix, that's essentially the column space. And then if they're linearly independent, then that also just so happens to be the image. And you can like sort of find the vectors that are like a basis for that image. Okay. So I did want to sort of touch on a bit of bases. Actually, no, before that, I should actually explain the dimensions of these. So I said that the kernel can be more of like multiple different like sizes or dimensions, and the image can also be of multiple different sizes and dimensions. As a result, we can actually name these sort of dimensions. We say that the dimension of the kernel is equal to the nullity. We call it the nullity of T, kernel of T. And the image, if I take the dimension of that, that's going to be the image of T, and we're going to call that the rank. So there's a lot of terminology you have to sort of remember, but these are important things to know because you'll be quizzed on them. But besides that, it's also pretty important to know. So that's called the rank of T. So we've got the nullity and the rank. Now, one of our most important theorems is the rank nullity theorem, which states that if you take this transformation, if you look at this transformation, if you look at the dimension of sort of your domain, so your input vector space, right? The dimension of that is equal to the nullity plus the rank. So the dimension of V, in this case it's V, dimension of V is equal to the nullity of T plus the nullity of, sorry, I said nullity plus nullity. The nullity plus the rank. And I'll be using this in the upcoming example. Now, there's one last bit of theory before I keep going. I actually start doing the questions, which I think you guys are probably hoping that I get to soon. So, before that, I need to talk a bit about bases. So, in general, whenever we've been understanding our vector spaces and our sort of our matrix or our linear transformations, we've done them with respect to like the standard coordinate system. So if you remember, maybe from high school, you were introduced to I, J, K. These were your like unit vectors in the sort of like 3 cardinal directions for R3. This is for R3. So this represents the vector 0, 0, 1. This represents 0, 1, 0. And this one represents 0, 0, 1. And so with these 3 vectors, you can get anywhere in 3D space. But we don't actually have to define our transformations and our coordinate system around this standard basis. There are instances where using a different sort of basis is useful, especially when you do things like specific transformations and you want to find the matrices of that. So if you do like a shear or if you do some sort of rotation matrix, it might be more useful to use a different basis. We don't actually have any examples of that, but if you go into it was chapter 3, it was around the end of chapter 3, there were examples of shear transformations, and one of the examples made by the lecturer used a different basis in order to solve the question because it's a lot easier to do. So what you can do is that if I had like a basis, let's just say I used what sort of vectors? 1, 1, 2, 3, 4, 8. I just hope that these are actually linearly independent. And maybe 0, 0, 1. So if you take these, right, this could be your basis. The 2 conditions for it is that these have to, A, span the vector space that you want them to span. So I want them to span R3. So this has to span R3. And they have to be linearly independent. Those are the 2 conditions to get your basis. And so from these, you can sort of create a relative coordinate system using coordinate vectors. So if I have that basis, actually, let me go back. If I have this basis right here, if I wanted to find some vector, let's just say 5, 3, 2, if I wanted this with respect to the standard basis, when I do like this curly S, I mean the standard basis, well, this is quite simple. What you do is that you do 5 times I plus 3 times J plus 2 times K. And so it sort of immediately falls out that the answer of the coordinate vector to get to 5, 3, 2 with respect to the standard basis is 5, 3, 2. It's the same thing. But well, let's just say I wanted to find the basis with respect to call this B, or beta actually. Well, then what you would do is that you would take, you need to find what linear combination of these, what lambda 1, let me write that somewhere where it's more legible, out here. Then what I would want to do is I would do lambda 1 times 1, 1, 2 plus lambda 2 plus 3, 4, 8 plus lambda 3 is 0, 0, 1. So what I need to find is I need to find these three, call them lambda 1, lambda 2, lambda 3, that form this coordinate vector that allow us to get to 5, 3, 2 using our basis B. Sounds a bit convoluted, and some of you might be thinking, oh, why is this useful? Why can't I just use the standard basis? There are examples where using a non-standard basis are useful. If you want to do, let's just say, a projection onto some line here, so you have some sort of vector here, or some vector here, and I want to project that here, and I want to describe this by some sort of matrix. Instead of using the standard bases, I would use one that's parallel to the line and one that's perpendicular, and that'd be useful. That's just like a quick example. All right, I guess we'll just go through maybe the first question before we get to the questions, right? Okay, so the first question, it asks, we're given a linear map from R4 to R, and it's defined by this. We need to prove that it's a linear map. Okay, well actually, I shouldn't say it's a linear map. We've got some sort of transformation, and you make sure that it's a linear map. So how do we do that? Well, using the definition of a linear map. So this right here. I need a proof that the linear map or the transformation respects addition, vector addition, and scalar multiplication. So let's try that now. If I say, let's go here. So this is our T. Let x1, oh sorry, let's just call it x. Let x and y be elements of R4. Then, if I take the transformation of these, the sum of these, right? What does this give us? Well, this transformation is encoded by this rule. So what I'll do is that I could sort of substitute that in. We say that y, I'm sort of decomposing it into its components. This is x1, x2, x3, and this is y1, y2, y3. So what you get is you get x1 plus y1 minus x3 plus y3 plus 5 x4 plus y4. So what I can do is that I can split these up. I can say, well, x1 minus x3 plus 5 x4. And I can also say y1 minus y3 plus 5 y4. Now what are these? Well, these are actually in the form of this, but with respect to x and y. So this is t of x plus t of y. So perfect. This this transformation respects vector addition. So that's nice. Now we have to prove that it respects scalar multiplication. So let me just write a bit more to the right. Let's just let lambda be some element of R. Then what we can say is that t of lambda, what is it? We'll use x this time. We'll just use x, is equal to, well, what we do is that we would lambda x is going to be equal to lambda times each component. You can sort of see that like this. Actually, these are 4-dimensional, aren't they? It should be y4, and this is x4. My bad. But yeah, you just multiply each component by y. And so when you're writing out the rule, it's sort of in a very similar format. You do x1 of this minus, it would be lambda x3. Ooh, I am running out of space. Plus 5 lambda x4. And so I can take the lambda out, x1 minus x3 plus 5x4, and this is actually equal to t of x. Great. So respect scalar multiplication. Is that pretty straightforward, I hope? One good thing to sort of develop is like an intuition about what transformations are linear and what are not. What you can see here is that, I mean, in my case, just looking at this transformation, I can already tell you that this is linear without having to do the proof. And the reason for that is that this is a plane, essentially. Well, it's a hyperplane. It's a plane in R4, right? And so what you can say is that in most cases, if you have a transformation that only sort of adds components together, then you can sort of like already judge whether it is, you can judge that it's probably linear, a linear map. So this is a plane. So, I mean, this is R4, so I can't really draw it. But if it was R3, for example, if it was just a plane, something like this, this, and then I would have some plane that cuts through the origin, right? Well, then I can say that, oh, if I add any two vectors on this plane, well, then it'll give you another vector on this plane. And then if I scale any vector in this plane by some amount, I'm still on the plane. So you can already sort of like visualize the solution in your head. And so that's probably something that you might want to sort of like build as you do sort of these questions. It does come with practice. All right, so that's the first part. The second part of the question was I need to find a basis for the kernel of T and find a rank of T as well. The second part of this will actually follow from the first part. So back to the definition, what is a kernel? Well, a kernel, let me get rid of some of this so I've got more space to work. The kernel of T are all vectors, V, that transform into the zero vector. So what this is, right, is that, well, I've actually got it in terms of x. Let's call this x. Well, then this is going to be T of x, which is equal to x1 minus x3 plus 5x4 is equal to 0. So all the values in this transformation, right, that lie on this sort of hyperplane will converge to 0, essentially. All right, but what this asks is that we need to find a basis for this kernel. So we need to find vectors that when we sort of like multiply them by, we take the linear combination of them, it spans this plane. So one way we could do that is that we can sort of manipulate this equation. We can say that x1 is equal to x3 minus 5x4. And so what this means is that if I have x, some x, which is x1, x2, x3, x4, well, there is a restriction on what x has to be. X has to be x3 minus 5x4. For x2, well, x2 isn't actually in this definition of the transformation. So it's like a free variable, essentially. It's sort of like independent of them. So I can just leave that as x2. For x3, we've already sort of used this rule, so we just leave it in terms of x3, and this is x4. So what we have here is that we have like three variables, or three free variables, that we can use in order to create the span. So what we can say is that if I sort of break this up, I can do x2 times 0, 1, 0, 0 plus x3, which is going to be 1, 0, 1, 0 plus x4, which is going to be minus 5, 0, 0, 1. You see how I sort of did that? I just sort of took this and I expanded it with respect to the coefficients. And so what does this tell us here? Well, the basis, or sort of the plane here, or this hyperplane, is described by the span of these three vectors. And these three vectors are linearly independent. You can sort of already see that they're linearly independent because of all like the zeros and different things. You can't get the linear combination of one and turn it into the other, or they would have combined. So what we can say is that the basis of the kernel of T is going to be, well, it's just going to be these three vectors. 0, 1, 0, 0, 1, 0, 1, 0, and minus 5, 0, 0, 1. And then you take the span of these, and then that gets you the space of the hyperplane. All right. So the next part was asking, we needed to find the rank of T. Now, by the rank nullity theorem, this actually is pretty straightforward to find. What we can say is that, well, this transformation takes in values from R4 to R. So the sort of like your domain has a dimension of 4. So by the rank nullity theorem, we know that 4 should equal the rank of T plus the nullity of T. So if we want to find the rank, well, we need to know what the nullity is. But by the previous part, we do know what the nullity is. We find the nullity because what is the nullity? The nullity by definition is the dimension of the basis, the dimension of the basis vectors of a kernel, of the kernel. Well, we found the kernel here. How many vectors are there in this basis? Well, there's 3. So the nullity is 3. So this is 3. So the rank of T is necessarily 1. Because 1 plus 3 is 4. Nice. Maths. All right. So that's that question. Are there any questions about that before I move on? Nothing on the chat? Okay, that's good. All right. We just move on. All right. So the next question asks, we're given 2 statements. We need to show that if these statements are true or false. So the first one is V is the vector space of, or it's polynomial space of degree 2 or less. So these are going to be polynomials of T2, A plus, but it's going to be in the form of this. So all vectors in the form of CT squared plus, BT plus A. Why did I write 2 pluses? Plus A. So it takes in all of these vectors, right? So this is the vector space. And S is the set of these vectors, but these are written as polynomials, but they're really vectors. Then S is a spanning set for V. So I need to show that S is a spanning set for every vector of this form, essentially. So how can we do this? Well, we know that we've got 3 vectors here, right? We know that the dimension of P2, so the dimension of P2 is going to be sort of like how big this vector is. You can sort of see that the dimension of Pn is going to be n plus 1. This is a bit like maybe weird to think about, but if you have a sort of like a quadratic, right? Well, there's 3 sort of variables here, so it's really 3-dimensional. What we say is that in order to get a spanning set for V, we need to have at least 3 vectors, right, in S in order for that to be true. We have 3 vectors, right? But there's one caveat, and that's they have to be linearly independent. And the reason for that is that if they're not linearly independent, well, then we can throw out one of these vectors, right? Because that vector can be made by another 2. Let's just say if it is linearly dependent, then maybe this one can be written from these 2. Well, then now we only have 2 vectors, right? And so we can only span a 2D sort of surface. So that wouldn't work. So the only way that this would work is that all of these are independent. And so that's what I have to sort of show. If these are independent, well then, yes, they are a spanning set. If they're not independent, well then they don't span 3-dimensional space. Does that sort of make sense? Okay. All right. So how would we do this? Well, what we'd have to do is that we need to show that these are linearly independent. And so by the definition, we can do something like this. We can do alpha times t squared plus 3t minus 3. So I'm taking each of these vectors. This vector. I'm going to take this vector here, this one, and multiply them by some scalar multiple. And you need to show that the only solution for this that equals 0 is when alpha plus beta and I'm going to use gamma are 0. So let me just write this out. Minus 7t plus 8 plus gamma 3t squared plus 7t minus 8. So you show that this is equal to 0. Now, it's a bit ugly to work with them just as polynomials, so I'd rather use them in, I'd rather represent them as coordinate vectors, right, with respect to your R and dimensional vectors. And the reason for that is that I can do some nice Gaussian elimination in order to solve this. So what I can do is that I can represent this here as minus 3, 3, and 1. I can represent this as 8 minus 7 minus 3. What I'm doing here is that I'm going, each sort of power is sort of going down. So this one would be, the top one would be minus 8, this one would be 7, and this would be 3. So if I look at the sort of, if I make a matrix out of this, if I make some sort of equation, a system of equations, I can do minus 3, 3, 1, 8, minus 7, minus 3, minus 8, 7, and 3. And what do I need to show? That I need to show that this multiplied by alpha, beta, gamma is equal to 0. So in other words, I need to find, what is this really? I need to find all the values of this vector here, right? That gives us, that points to the 0 vector. So I'm really finding the kernel of this matrix. So I need to find the kernel of minus 3, 8, minus 8, 3, minus 7, 7, 1, minus 3, 3. And if there's only one distinct solution, well then I know that these are linearly independent, because the solution is going to be 0, 0, 0, or alpha is equal to 0, beta is equal to 0, and gamma is equal to 0. If there's infinitely many solutions, well then they're linearly dependent. And so the same would be false. All right, so in order to solve this, we'll do some row reduction. Gaussian elimination. Hopefully this one is nice. I'll go through this try to go through it a bit quicker, because I feel like you guys already know how to do Gaussian elimination. So what I'm doing is I'm just swapping these, and then what I can do, I can say that these are actually equivalent because I'm taking the kernel of them. So some nice notation that you might want to use when you're doing your questions. What I can do is I'll do 1 minus 3, 3. This one is going to be 0. This one's going to be this minus 3 times that. It's going to be 2. And then it's going to be minus 3. It'll be minus 9 plus 7 is minus 2. Okay. And then this one's going to be 0. This one's going to be minus 3. This is going to be minus 1, I think. And then this will be minus, this is going to be 3, which is going to be 1. Okay. And this is going to be equal to kernel of 1 minus 3, 3. We can see that this is a scalar multiple of that, so I can eliminate one of these. Well, I can already tell what the solution is, but I'll make it a bit more clear. So what we can see here is that we have this row-reduced matrix. We have 2 leading columns, but 1 non-leading column. So there are infinitely many solutions, and so they are not linearly independent. And so if that's the case, they are not linearly independent, well then they can't span V. So the answer to this is, do they span V? False. Incorrect. Does not work. So that's 1. All right, so the next part, let me clear up some of this so I can work on the next part of this. Okay. So for question 2, we are given a transformation that takes square matrices of dimension 5, 5, or 5 by 5, and gives us a vector in R2, and it's defined by this rule. I need to show that this is a linear map. Okay. Now, I'll ask you guys a question. Looking at this map, do you have like a gut feeling about, is this a linear map or not? Is there maybe one part of this linear map that might be a culprit in not being a linear map? Any ideas at all? Maybe I should like define some of these. So what is TR? TR is called the trace. So the trace is an operation that you can do on a matrix. So what it is that if I have A, B, C, D, all right, it has to be for a square matrix. That's why we're given 5, 5, conveniently. The trace is going to be equal to A plus D. So it's going to be the addition of all the diagonal. And then if it wasn't 5, 5, it was n by n, then you'd go down the whole diagonal. So that's the trace. And DET is the determinant. So the determinant of A was not really a very nice way of showing this in generality, especially for 5 by 5, it's not very nice. Later down, I have a whole slide, because all of chapter 5 is dedicated to determinants. These are some of some of the properties of determinants. Maybe pay special attention to this one right here. So keeping this one in mind, if a row of A is multiplied by a constant alpha, the determinant is also multiplied by alpha. Now keep that in mind. If I go back to this, well, before even doing any calculations, I can say that this is most likely not a linear map. And the reason for that is because while trace might look okay, I can add 2 traces together, and the sum of the traces is the trace of the sum, right? So that's fine. You can sort of like see that in your head if you add 2 vectors together. If you split them up again, right? The diagonals, you just sort of like conserve the addition of the diagonals. So everything sort of makes sense. But the determinant is odd. The determinant does not play nice. It's ugly. I personally hate it, but it's important. And the reason for that is that the determinant does not play nice with a lot of linear operations. And if I give you the example, if I use that property that I showed you before, what it would say is that this, actually, let me write that up again. The determinant, if, let's just say I wanted to disprove this, well, one idea is that I could check for scalar multiplication. If scalar multiplication is respected, well, what would this mean? So if I've got some t, t times lambda is going to equal, well, what I can do is that I'll put this into this form. So it'll be tr of lambda a minus 2 times the determinant of lambda a. I was going to write it. And then tr of lambda a. So how can I manipulate this? So I can make it look like it's a linear map. What I can do is we know that traces, if I multiplied the diagonals of a matrix by some lambda, I can just take that common multiple out. And so it is linear in that regard. So for traces, everything's a-okay. I can do alpha times tr of a minus 2. Now, but for the determinant, if I'm multiplying a by a multiple lambda, well, from the property that I showed you before, if I want to multiply one of the rows, just one of the rows of the matrix A by some lambda, then I have to multiply the whole thing, or the determinant of that is also multiplied by lambda. So what really happens is that the determinant of lambda A is actually equal to the determinant of the dimension of A. Now let me just draw this out so it's actually very clear. Lambda times tr of A. So what this tells us is that if I have some A, B, C, D, if I multiplied this row by lambda, for example, right? Well then the determinant of A, B, C, D, right? If this is like the determinant of this is going to be equal to some like D, right? If I take the determinant of this is equal to lambda times the determinant of D, or it's actually going to be we'll just call it lambda times D. Just by taking out the lambda from one of the rows. But what if I'm taking lambda out of all of the rows, right? Well, then I'm taking out lambda from, let's just say this is maybe some mu. So if I'm taking out lambda from this row, I'm taking out mu from this row, it will be lambda times mu. And so if I did this, if I kept, so I should draw it down. If I kept doing this, E, F, G, H, if I had some gamma, if I had some, not mu again, alpha, I don't know many Greek letters, I keep reusing the same ones. This one's equal to mu, lambda, gamma, alpha, D. So you're just sort of taking them out from each row. And so you can imagine if each of those rows were multiplied by lambda, well, it will just be all of these would be lambda as well. So it would just be lambda times the dimension if that was n, but our dimension is 5. So let me just do a quick check. Okay. So this would actually be 5. Actually, no, not on this direction, on this side. This would be times lambda to the 5. Okay, so what this tells us is that this is the same thing as lambda times tr of A minus 2 lambda to the 4 det of A tr of A. Now this is not in the same form as we saw previously. There is an extra lambda to the 4 multiplied by this det of A. And so you can imagine that for certain values of lambda and certain values of A, this might not always hold to be exactly the same as the definition. Well, I mean, one example you could do is A is equal to the identity matrix when it's 5 by 5, and lambda is equal to 2. I won't show it here, but you can already maybe see that that's true, that this would sort of contradict the linearity principle. So yeah, when you start seeing things that when you start seeing multiples to the powers of things, or sort of coordinates that are multiplied together, then you can already sort of see that, oh, maybe this isn't linear. And so you can easily find a contradiction. It shouldn't be that hard to find a contradiction. So I'll just say one of the contradictions is let A equal I and lambda equal 2. You don't want it to be equal to 1 because, well, if lambda is equal to 1, well, then it'll be exactly the same. But when it's 2, well, what will happen is that this will blow up. This will be 2 to the 4, which is 8, 16, I don't remember. And then it wouldn't be of the same form anymore. So that's that question. Are there any questions about this before I move on? No? Okay. Okay, this one. So, we're given a set of polynomials of P2 that follow this rule, which is a subspace of P2. We need to find a basis for S. Okay. Well, what do we know? We know that P2 is all the vectors of this form. PT, actually let me rewrite that. A plus BT plus CT squared. And so I need to find what form, what sort of like subset of this would agree with this condition. So if I let this equal to P, well, if I take P and I evaluate at -2, what I would get is I would get A plus B times -2 plus C times -2 squared, plus we need to find the derivative of P. So the derivative of P would be B plus 2CT, evaluated at 1. So it would be plus B plus 2C. So this is the same thing as A minus 2B plus 4C plus B plus 2C, which is equal to A minus B plus 6C is equal to 0. That's the condition. That looks like a plane. A, B, C, they're all linear combinations of each other. This looks like a plane. But that's not enough. We need to find a basis for them. So we need to find 2 vectors, right, that would represent this. So, an easy way to do that is I would reorganize this much in the same way that we did the example above. So let A is equal to B minus C by rearranging that equation. And so for some vector A, B, C, well, we can rewrite it as B minus 6C, and then we would have B and we'd have C. So we sort of break that apart again, as we did before. What we'd have is that we'd have B times 1, 1, 0 plus C minus 6, 0, 1. Is that right? That's right. And so these 2 vectors are our basis. They're linearly independent. There's 2 of them, and that makes sense because our subspace is a plane. So we need 2 linearly independent vectors, and they sort of go whichever direction, as long as they're linearly independent, and then they span the whole plane. All right, so that was that first part. Second part was now let T be the map from P2 to P1. And what we need to find is that we need to find the matrix for T with respect to the standard basis for P2 and P1 in the domain and the codomain respectively. Okay, so as I said earlier, you can turn any map T into a matrix of A times some vector. So what we can say is that if I want to find this A, how do I do that? Well, we're given that we want to find them with respect to 2 bases. So that would be P2. So the standard basis of P2 is, well, in polynomial notation, it would be equal to, we'll call this that. This would be 1t squared. Can you guys kind of see how this is like a standard basis for P2? Hopefully. And P1 would be this. So this is like your I, your 1 here is like your I, and this is like your J, and this is like your K, essentially. All right. So if I want to find the matrix, well, I know that T of some V with respect to some basis, codomain basis B, is equal to A with respect to some times by a vector with respect to some, let me change these, with respect to some basis B, and this with respect to some basis C. Now, what I can say is that if I make B the standard basis, then if I put in 1, what would happen? Well, then this would become the coordinate vector 0, 0, 0. It would be that. And so what that gives us is that this will give us the first column of A. And this would actually be the transform version of this vector with respect to C. And C, we've said, is S in terms of S1. It was just the standard basis as well. So it's actually quite convenient. So all I have to do, if I want to find A, is that if I've gotten this basis here, the standard basis, I'll input each vector from this basis, 1 by 1, put them into the transformation, see where they land, and that becomes the new the column, the respective column of that matrix. And so I do that for each of these 3 vectors. All right, so let's do that. It's a lot of clutter. Okay. So what is T? T is, oh, actually I had the, oh no, it's a different it's a different thing. Okay, that's fine. Yep. So what we need to find is that we need to find T of 1 first, because that's the first, this is this thing right here. All right, so what's T of 1? Well, T of 1 is, we need to find 1 evaluated at -2, which is just 1. We need to find 1 evaluated at 1 times T, which is just T. And then we need to find the derivative of 1, which is 0 times 3, which is 0, plus 0. If I wanted to write this as a column vector, so if I wanted to write this with some as a coordinate vector, I would do 1, 1, 0. So that's for T1. If I wanted to put in this, the second vector in the standard basis, T, what would happen? Well, we'll evaluate T at -2, so that's -2. We'll evaluate T at 1 times T, so that would be 1 times T, which is T. Yes, that makes sense. And then the derivative, the next part would be taking the derivative of T, which is just 1, times 3, which is 3. So this is equal to 1 plus T again. That's nice. So that's 1, 1, 0. Okay. And then the last part is finding T squared. How am I doing for time? Okay. You find T squared. So I need to evaluate T squared at -2. T squared at -2 is 4. What is T squared at 1? Well, that's going to be 1 plus T, or it will be multiplied by T. And then the derivative of T squared, well, that would be 2T times 3, which is 6. Which is going to be 4, 1, 6. So these are the columns of A. So if I wanted to find the matrix A, it would just be 1, 1, 0, 1, 1, 0, 4, 1, 6. Okay. Are there any questions about this? So this is the matrix with respect to the standard basis for P2 in the domain and P1 in the codomain. Okay. Now, next part. Now we've got an A. Now we need to find the matrix of T. So we need to find another matrix of T. Let's call it M. We need to find some matrix. Let's call this M. With respect to, that's not a good arrow. Just some T is some M. With respect to P2 in the domain, so it's the same, but our codomain is with respect to a different basis. Now this makes things a bit complicated. The best way to go about this is using a commutative diagram. And so what you can do is that you can do change of bases pretty fluidly, because going from a non-standard basis to a standard basis when you're doing transformation is fairly straightforward. Going from a standard basis to another standard basis is also very straightforward because we just did it. But going from a standard basis to a non-standard basis is ugly, because then we would have to, as I said a bit earlier, if I can find the slide. Yeah, I would need to find lambda 1, lambda 2, lambda 3. So I'd have to solve some sort of matrix. And I have to do that for each vector that I put in. So I might have to solve 3 matrices and find their kernels in order to find the coordinate vectors that I want. So it's a really big hassle, and you don't have the time to do that. So you'd use what you would do is that you'd use a commutative diagram. So let me sketch one out. What do we have? Let me just save that value for A, just so I don't lose it. Let me just write that a bit higher, and then let me get rid of some of the stuff below. Okay. So let me draw the commutative diagram. So what we have is that we want to go from P2 to P1. And we want to do this via T, or some matrix M. But this P2 is with respect to S2, and this one is with respect to some basis, was it B? Yeah, it was with respect to a basis B. Okay, now if I wanted to do this, I could go the straightforward way, which would be difficult, or I could do it a different way. I can go into P2, right? And I'll just, it's a bit relevant for me to draw this, but I'll just draw it this way because it's the standard way to draw it. I could have some identity matrix that maps P2 with that standard basis to itself. So it's a bit redundant, but just bear with me. And then I could have another matrix that maps from P2 to P1 using the bases S2 and S1. And then, then another way, it's another thing that you would have to do as well is that you would have to define from S1 to B, but that would be a bit complex because that's sort of the same issue that we have. So we'll define B to S1 to be another matrix. We'll call this Q. And so that takes you from P1, from the basis of B to S1, or it takes you to P1 with the basis of the standard basis of 1. Now the interesting thing though is that if you look up here, if we go from P2 to P1 with respect to the standard bases, well, that's just what we did earlier. This is A. So what I can say is that if I want to find M, what I would do is that I could do M is equal to, remember how matrix multiplication works? It sort of builds up from the right. So I would apply the matrix P. So I'd go up, let me use a different color so this is clear. So what I would do is I'd go up here, I'd go this way, and then I'd go down here. That's the same as going here. So what is that? So that would be P. So I'd take P, And then from P, I need to take A. And then I need to go down to B using this. But it's in terms of Q, but Q is invertible. So I can make this Q inverse. All right. And now this makes finding M a lot easier. And the reason for that is that we already know what A is. Well, A is just this, what we found earlier. P is the identity matrix from P2 to P2 with the same standard bases. Well, that's just the identity. So that would be fairly simple. P would just be I. And this would be, it would be a 3 by 3. So this would be a 1, 0, 0, 0, 1, 0, 0, 0, 1. So really you can just sort of ignore it because any matrix multiplied by the identity is the identity. So this is actually just equal to Q inverse of A. You can ignore P because P doesn't matter. And how do we find Q inverse? So what we would do is that we need to find the matrix that represents the finding from P1 to P1, okay, from the bases B to the standard basis. So what would that be? Well, we know what B is. B was given to us. B is going to be 1 minus 2t. And what was the other one? 1 minus 3t. So if I wanted to represent these as a matrix, well, what I could do is that if the output's going to be in the standard basis, well, what I could do is I would say that Q is just going to be these vectors represented as columns. You see how I sort of did that? I just sort of turned these into these vectors, 1 minus 2, and this one into 1 minus 3, and I turned these into the columns. And so this is how they land in the standard basis. You'd see them as 1 minus 2 and 1 minus 3 coming from the basis B into the standard basis. Okay, so that's Q. We don't want to actually find Q though. We want to find Q inverse. Q inverse would be the determinant of this. So this would be minus 3 times, it would be minus 3 minus 5. So it would be 1 on minus 5 times, what I'd do is that I would flip these two, and then I would take the negative of this. And so that would be Q inverse. And so now I have Q inverse, and I've got A. Then if I wanted to find M, I'll just do matrix multiplication. I'm not going to do that here because it will be very, very tedious and it would take a long time. But this is still a lot faster than the other way, the original way. So you just you find Q, and then you'd do Q inverse, and then you would do Q inverse would be 1 minus 5 times minus 3, 2, minus 1, 1, and then multiplied by, what was A? 1, 1, 4, 1, 1, 4, 1, 1, 1, 0, 0, 6. So you just take the product of these, and this is equal to M. That's how you'd find M.
Can those matrices multiply together? Is there different sizes, right?
Ooh, you are right about that. Did I make a mistake here?
It's in P2, even though it's
Oh, you're right. Hold on, sorry. Let me erase. So it went from, so that's P1 to P1, and then A would not be, I did make a mistake with A somehow, because that's not supposed to be, A is supposed to be, let me see what I got here in my notes. I did do this earlier. I think I might be farting right now. Okay, so the A that I got was, okay, yeah. Okay, so I did get a wrong. It wasn't 4 it was actually, it was a 2 by 3, and that makes sense. Sorry about that. A is going to be a 114, 117, and the reason for that, actually, if I go back, I did do the previous part a bit wrong. The answer for this part, where was it? I think I might have rubbed it out, but I kept the third column there, which was the third row there when it wasn't supposed to be there. It was actually just supposed to combine into just the first and the second row. And then you can multiply these, because it'd be 2 by 3. Actually, it'll be 2 by 2 times 2 by 3, so that you get a 2 by 3. So you'd have a matrix that is Q inverse is 2 by 2, and A is 2 by 3, so your M would be 2 by 3. Okay. Was that all for this? Ooh, I also did another arithmetic mistake. It was actually when it came to the inverse. That was my bad though. So Q is actually correct, but Q inverse is not correct. And the reason for that is the determinant of this would be, of this matrix would be -3 minus -2, which is -1. So it would actually be equal to -1 times -3, 1, -1, 2. There we are. And then you do the multiplication that way. And this would be Q inverse. And so you do Q inverse times A, and then you find M. All right. I guess we'll move on. All right, so chapter 4. So chapter 4 is all about orthogonality, so finding orthonormal bases and doing solving questions by the method of least squares. So one of the big things is using the Gram-Schmidt method, or the Gram-Schmidt process. And so what that is that if you're given a basis or a linearly independent set of vectors, you can turn them into an orthogonal basis using this algorithm. So you would take the first vector and you'd make that part of the set, and then you take the second vector and then you remove the contribution of that vector. You remove the contribution of Q1 from that vector, and then that would become your second one in the basis, and you just keep doing that as long as you have to Qn. Now, this would make all the Qs orthogonal, but wouldn't actually necessarily make them orthonormal. And so what you'd have to do is that you'd have to normalize all of them. So you'd have, if you want to make them a unit vector, so use a unit vector, it would be from Qi, and you divide it by Q, by the magnitude of Q. And so you do that for all the vectors, and then it will become unit size. And so that would be the Gram-Schmidt process. Does anyone have any questions about how to do this algorithm? Most of the time, you won't get questions that have more than maybe 3 vectors, because it doesn't get quite long and tedious of having to have to do all these projections and then subtract them away from the vector, your original vector, in order to find the orthogonal vector. But that's the process right there. Okay. So we have a question here. It says we're given a matrix A. We need to find the QR factorization of A. So we need to find 2 matrices that multiply together, give you A, but there are 2 conditions on these matrices. One is that Q has to be orthonormal, So, or all the columns have to be orthonormal, and Q has to be orthogonal, I guess, which is necessarily true. And R has to be upper triangular. So what that means is that R, if this is some square matrix, you would have some A, B, C, 0. So you would have sort of non-zero entries on the top right side of the matrix until the sort of like the diagonal line, and then everything below that would be zeros. So we need to find a factorization that's true for this, and then after that we need to find a basis for the image of the find basis for the perp of image A. So this would be the orthogonal complement, and I can explain a bit more about that once we do the QR factorization. Okay, so we want to do the QR factorization of A. Well, what we have to do is that we're given, I guess you can represent each of these columns as some vector. I want to find u1 and u2 that span the same vector space as v1 and v2, but they are orthonormal. And so how would I do that? I'll use Gram-Schmidt. So what I can say is that in order to find u1, let's just use some intermediate q1 and q2, and then I would normalize them at the end, and then I would go. So I would go from here to there, and then from the q vectors, I'd move down to the u vectors. So I would apply Gram-Schmidt. So what I know is that q1, well, let's make that equal to the first vector in the set. We'll just pick one. We'll just do v1. So q1 is equal to v1. That's the first vector. Now I need to find another vector, q2, that is orthogonal to q1. So in order to do that, I can take the second vector v2, and I can subtract the projection of v2 onto q1, and that'll give us q2. So first of all, I know what v1 is. v1 is 8 minus 4, 4, 2. I also know what v2 is. v2 is equal to minus 12, 6, 4, 2. Now, this is subtracting the projection. Now, the definition of the projection is, hopefully you remember this from first year, that would be q1 dotted with v2 over the size of v2 squared multiplied by v2. Okay, so what is the value of this? So this would be minus 12, 6, 4, 2. Now the dot product of q1 and v2, so it'd be the dot product of these two vectors. And so, well, these are not very nice numbers. I'll use my calculator. You have access to a calculator in the exam. So if you want to do fast multiplication in your head, you're free to do so, but I'm not someone who can do that. Minus 4. So I'm just taking the dot product of v1 and q2. So you do 8 times minus 12, minus 4 times 6, 4 times 4, and 2 times 2. What is going on here? This would be minus 6, hold on, 8 times minus 12 plus minus 4 times 6 times 6 plus 4 times 4 times 2 times 2, which is minus 100. Interesting. And the denominator would be the size of q2 squared. I can try doing that in my, actually, no, why bother? So I'll take the dot product of that with itself. So it would be 8 squared plus 4 squared plus 4 squared plus 2 squared. Oh, it'll be 100. That's nice. And then V2, what's V2? We know what V2 is. V2 is going to be, was it V2 or V? No, it was actually Q1. That was a mistake. This is Q1. And this would be Q1. So multiplied by this, 8. But I did the correct arithmetic. I mean, well, V1 and Q1 is actually the same, but I'd rather write it this way. 4 and 2. This would be equal to minus 12, 6, 4, 2. This actually cancels quite nicely. This is 8 minus 4, 4 and 2. So this is equal to minus 4. This is equal to 2. This is equal to 8. And this is equal to 4. All right, so that's Q1 and Q2. All right. And so if I want to find the orthonormal basis, well, I just need to normalize Q1 and Q2. So U1 is going to be Q1 divided by the size of Q. That's going to be, well, that's 8. So that'll be just the square root of 100, which is 10. So that would be 1 on 10 times each of these. And 2. And then U2 would equal 1 on 10. I think it's also 1 on 10, isn't it? Because it's 4, 2, 8, 4, 8, 4, 4, 2. Yeah, okay. So there's the same number of those numbers, so I know the magnitude will be the same. And that would be minus 4, 2, 8, 4. Okay. So that gives us our Q. So if I write that down, our Q, which is our orthogonal matrix, which is also has entries that are orthonormal. This would be that minus 4 on 10, 4 on 10, 2 on 10. This would be minus 4 on 10, 2 on 10, 8 on 10, and 4 on 10. And so what I've done is I've just made this U1 and U2. Okay, so I have Q. Now, how do I find R? Now, to find R, we know that A is equal to Q times R. A is equal to Q times R. Well, what do we know? We know what A is. A is equal to 8 minus 12 minus 4, 6 is 4, 4, and 2, 2. And that's going to equal Q as a big matrix. I can get rid of a multiple of 2, but I feel like this might be useful in a second. Yep. 2 on 10, 4 on 10, 8 on 10, 2 on 10, and 4 on 10. Okay, so now we need to find a square matrix, R, that makes this right-hand side equal to the left-hand side. Now, there is an algorithm you can follow to do this, but for this question, you can sort of actually kind of read it out, really. What you can see is that, well, we know that this is going to have some entries, but this bottom left entry has got to be 0, because it's R. Now, how can I make this vector here, 8 minus 4, 4, 2, from this one and 0 lots of this one? So it would just be this vector multiplied by, well, what is it, 10, will actually give us this one. And so you sort of read off the solution that this, in fact, has to equal 10. Now, how do we do the next part? Well, this one is not as easy to do because it's not, none of the entries have to be 0. So, what sort of combination of these two would give us this? Well, looking at it, if I multiply both of these by, or this one by 10 and this one by 10, if I multiply this by 10, multiply this one by 10, I would get, if I look at the top row, I would have 8 minus 4. Well, what I really want is I want to get minus 12. So I could do minus 8 minus 4. That would work. So this would be maybe minus 4, minus 10. I just got to check that the other rows work. So that would be 4 plus 2, which is 6. That's correct. You would have minus 4 plus 8. Sorry, it was minus 4 plus 8, which is actually 4. Yep, that works. And you'd get minus 2 plus 4, which is 2. Yep, that works. So you just sort of like read out the solution to yourself, which would be a bit quicker than maybe following an algorithm. You can say that this has to be R. That's your QR factorization right there. Are there any questions about how I did this? So yeah, this is Q, and this is R. Okay, now we need to find a basis for the image of A that is, well, perpendicular to it. So what we want to find is that we want to find maybe like a family of solutions. We'll say some solutions X, from X1, maybe X2, how many, well, there's 4 rows. We'll do X3, X4, okay, such that they are perpendicular to the vectors that are outputted by A. Well, the vectors that are outputted by A are these ones. Or actually, if I wanted to actually maybe use the result that we just found, we want to find the values of X that are perpendicular to these two vectors, because these are orthonormal bases for this same space. So what I can say is that if I have X and I dot it with U1, which is one of the vectors in the bases, well, this has to be 0. It has to be perpendicular to that. And X also has to be perpendicular to U2, which is the other vector. And this pretty much describes the whole space that is spanned by U1 and U2. So how do I do this? Well, I have the form of X and I have U1. So if I do the dot product between them, I would get 8 on 10 X1 minus 4 on 10 X2 plus 4 on 10 X3 plus 2 on 10 X4. Is equal to 0. This has a common factor of 2 on, this would have, well, I can just simplify this actually, and then I can multiply the 5 after. So I'll do 2 on 5 X1 minus, actually it's not 2 on 5, this is 4 on 5. This would be 4 on 5 minus, this would be 2 on 5 X2 plus, and then this would be 2 on 5 X3 plus 1 on 5 X4 is equal to 0. I can multiply everything by 5. 4x1 minus 2x2 plus 2x3 plus x4. So that's one of the equations. The other equation is somewhat sort of similar. What I can do is I'll just sort of skip some of the working out and I'll just sort of give the solution. minus 2x1 plus x2 plus 4x3 plus 2x4. So our solutions for, or our solutions that give us the basis for IM perp, or IM of A perp, would be the solutions for this. So these are like hyperplanes, and we find essentially when these are equal to 0. Now, to do that, well, we can sort of encode that into a matrix. We would have, if I write this as similar linear equations, but in a matrix, I would do 4, minus 2, 2, 1. This would be minus 2, 1, 8, 2.
Ladies, it should be 4 as the 8.
Sorry, where was 4 as the 8 for the second equation? Oh, you're right.
Yeah.
It took me a while to see it.
Yeah,
It's 4 right here. This 4. There we are. And this should be 0. So you just need to find the kernel of this, and then that would give you the basis. Should probably just maybe, I could row reduce this, or I can just sort of give you the answer. So the answer to this was, if I did row reduce it, did I have it here? I think I did. Or if I just remember maybe the solution, it was equal to, oh, there we are. It was going to be 2 minus 1, 0, 0, 0, 0, 2, 1. Is that correct? This would be 4 minus 2, 2, 1, minus 2, 1, 4, 2. Yep, that works. So that's the row reduced form. So just assume I did the Gaussian elimination. I think you might actually have access to Maple during the lab exam. So if you wanted to maybe use that to do your Gaussian elimination for you, that might be a creative thing to do. But yeah, so you would have, get this matrix, and you can sort of read out the solution. So what we'd have is that x3 is going to equal to minus a half x4, and then x1 is going to be equal to a half x2. And so if I wrote that again, I can get this as a plane, because x1 would be half x2. This is still x2. This would be, x3 would be minus a half x4, and this would be x4. So if I split this up, as I have before, this is a half, this is 1, this is 0, 0, and this is going to be x4, and this is 0, 0, minus a half, 0. There. And that would be your basis. So you take span of these, and then this would be your basis for, for IM A perp. Are there any questions about this? I guess not. All right. So the next part, which was I need to find a parabola which best approximates these 4 solutions. Now, this uses the method of least squares. I can maybe explain a bit of the theory behind it, because I didn't beforehand, but let me start like structuring this question. So we know that y is given in the form, or y is given as mx squared plus bx, and we have certain pairs of xy. So if we just evaluate this equation, at each of those pairs, we would generate a bunch of equations that we can use that sort of constrain what the solution has to be. So if I try that, what I get is, put that away, if x is equal to 0, well, okay, you already see there's some arithmetic errors here, but that's sort of expected. 0 plus 0, because x is equal to 0 and y is equal to 4. 4m plus, if I substitute x is equal to 2, this would be 2b is equal to 6. And then I would have also, if I substitute 1, m plus b is equal to 6. And then it was going to be, the last one is going to be also m plus b is equal to 4. Now you can already see here that there is no solution to this. You can already see from the first line that 0 can't equal 4. Also, but you can also see that like, m plus b is equal to 6, but it's also equal to 4. There's a lot of contradictions here, and that's sort of expected. This is what we would usually call like an over-constrained or over-determined system. There's more constraints than there are free variables, and so there's going to be a contradiction there. And so that tells you that there's no perfect parabola that that sort of fits through all of those points exactly. What we want to find, though, is that we want to find a solution that is closest to each of those points. So if I rewrite this, this is 0m times 0b. I could rewrite this as a system of equations. I could do 0, 0, 4, 2, 1, 1, 1, 1. And then this would be multiplied by bm or mb. And this would equal 4, 6, 6, 4. Now this, this is still not true, but this is of the form of let's call this x is equal to y, where x is equal to mb. Okay, now we know this has no solutions, but if we bit clever, we could think about maybe another solution for y, or another value for y that would work. Let's call that z. So z is a solution that would work for ax is equal to, or a times x is equal to y, where ax is equal to z. So if I rewrote this, instead of y, let's picture another solution to this equation. Now, how would we find z? Well, the solution that best approximates y would be the one that projects y onto the reachable values of a, because a can't reach all values. A won't reach the value of y, for example. But there is a value that is closest to it that is reachable. And so what that would be is that if you would take the column space of A, you take the column space or the image of A, right? And then you would project the value of Y onto the image of A. And this would give you Z. Now, why is this true? You can probably think back to maybe first year maths when you did sort of like finding the closest like distance between two skewed lines. And so that would be the point that's perpendicular to both of them. It's sort of like the similar maths to that. But yeah, I won't go into like too much rigor about exactly how it works, because it's not actually how we're going to solve this problem. I'm trying to give you maybe the intuition about how you would solve it from a pure like theoretic standpoint, or like an intuitive way. And so you'd generate a z where ax is equal to z is a solution, and then you just find the values of x or mb that would satisfy that. and those would be your coefficients. Now, we're not going to do this because it's really, really tedious and long, and you don't have time for that. In the lecture slides, there is we weren't given I don't think you were given a derivation, but there is a condition where if y is not a solution, or it is not in the column space of this matrix, you can generate a solution, right, that's closest by means of least squares by solving this equation. And this helps. Now, how is this derived? I'm personally not too sure. My guess is that when you're taking the transpose and you're multiplying that by y, it's almost like you're taking the dot product of y with each of the columns of A. And so maybe it's got something to do like leveraging some sort of orthogonality principle. But nevertheless, this is true. And after this is pretty much just plug and play. We're sort of running out of time, so I might not actually do this computation, but how you would do it is that, well, we know what A is. 0, 0, 4, 2, 1, 1, 1, 1. We'll take the transpose of this. So we'd have 0, 4, 1, 1. We'd have 0, 2, 1, 1 times x, and that's going to be equal to 0, 4, 1, 1, 0, 2, 1, 1 multiplied by y, where y was 4, 6, 6, 4. Does this work? Yeah, it does work. So what you do is that you'd compute this, and you'd compute that, and then you'd augment it, and then you would do some matrix like this, and then you would find the solutions for x, which is m and b. And that's your solution right there. So I won't do that because multiplying these out and then doing the row reduction would take a really long time, at least the time that we have now, but that's the principle behind it. Okay, so moving on. So the next part was about determinants. I already sort of covered these a bit earlier. Some of the properties of determinants, such as the ones that don't make it very conducive to like linear maps. Things like multiplying a row by alpha means you multiply the whole determinant by alpha. Some of the properties are nice, like the determinant of the transpose of A is the same as the determinant of A. You can also expand determinants regardless of in any way you want. You can do it like row-wise, or you can do it column-wise, or you can pick some column. It doesn't have to be the first row or the first column. These are all in the lecture slides, so I won't go over them too much, but that's like the idea. What else? The determinant of the, if one of the rows or one of the columns is 0, well then the whole determinant is 0. Well, that just follows on what I said earlier. If you expand it across that column that is 0, well then the determinant has to be 0. So that's pretty nice. One of the other things, it's actually not here, but I might state it, that the trace of a matrix is equal to the sum of its eigenvalues. We haven't gotten into eigenvalues and eigenvectors, but this is true. 2 plus whatever. We also know that the determinant of A is equal to the product of eigenvalues as well. 3. That's also useful to know. All right, so I guess we'll move on a bit. Eigenvalues and eigenvectors. So eigenvalues and eigenvectors, the way they work is that if you have some sort of linear map and you take in some value x, if the image of that vector is the same as a vector but spanned along that same length, so all you've done is just sort of stretched it, then it is an eigenvector, and the ratio by which it stretches is the eigenvalue. Now, you can have multiple eigenvalues and multiple eigenvectors. For those eigenvalues, if you have multiple eigenvectors for an eigenvalue. That's called an, well, that would be, they would form an eigenspace. So that's something to keep in mind. Usually we don't actually like to write it in this form because it's not that useful. We could rewrite this as ax is equal to lambda x, which is equal to lambda I times x. I'm just adding the identity here just to make things a bit more matrix friendly. So if I just manipulate this and I move this to this side, I'll get ax minus lambda I x is equal to 0. So a minus lambda I times x is equal to 0. And this is much nicer to work with. What we do is that, well, what values of lambda here would give us, would take us to 0? Well, that would be the values that are invertible, which would mean that the determinant has to be 0. So if the determinant of this minus lambda I is equal to 0, well then the value of this lambda is an eigenvalue. And then, well, from this you can see that, well, what sort of matrix here, we want to find the x that would make this true. Well, that would just be the kernel, because it's all the vectors that, given that matrix transformation, would set it to 0. So that would just be the kernel. So a minus lambda I would would give the eigenvectors, or equivalently the eigenspace. Okay. Any questions about that theory? No? Although, this is pretty much just in your lecture slides, but we'll just rehash it a bit. Now, diagonalization, this is actually quite important. It will be more important later on in the course when we're taking powers of matrices and when we're doing like the exponential of a matrix. The diagonal matrix space is like pretty straightforward. It allows us to compute these actually quite nicely. But for now, our definition, all we have to worry about is the definition of a diagonalized matrix. So what we do is that if I have some matrix A, right, then if and only if the arithmetic multiplicity, I'll get to what that means, of some eigenvalue is equal to the geometric multiplicity of the eigenvalue, then a matrix is diagonalizable. So what does this mean? So the arithmetic multiplicity is the polynomial that's generated by this determinant. So if I have something like this, lambda minus 2 squared is equal to 0, well, this has multiplicity 2. Multiplicity 2. And this has multiplicity 1. And so this would be the arithmetic multiplicity is 2, arithmetic multiplicity of this eigenvalue, which is 3, and this is 2, are going to be what they are. The geometric multiplicity is a bit different. That's the dimension of the eigenspace. So when we have this set of vectors, right, we need to find how many vectors are in that space, or that sort of like basis, almost. If that eigenspace has one vector, for that one eigenvalue, well then we say that that eigenspace has a geometric multiplicity of 1. If it has 2 vectors, it's 2. If it's got 3 vectors, it's got 3. The important thing is that they have to be equal. So the amount of powers of lambda here have to equal the number of vectors in the eigenspace. So that's that. If that is the case, then we can say it's diagonalizable. And what this says is that if I have some matrix A, and I have some invertible matrix P, and P is the matrix of the eigenvectors in some order, well then D is going to be a diagonalized matrix of the eigenvalues of that matrix. It's probably best if I just write it out. So if I have some matrix A, I don't really care what it is, and I have some vector, I'm just going to construct these out of thin air. Let's just say this is the case. So let's just say also, and then D, which is, let's just say this is equal to 1, 0, 0, 5. Actually, no, that's a bad example. It has to be equal, doesn't it? 1, 1. So what does this tell us? This here is one of the eigenvectors. This is also an eigenvector. The eigenvalue of this vector here is 1. The eigenvalue of this vector is 1. Actually, no, let's make that 2. Let me rub this out. So these have multiplicity 1. Yep. So the eigenvalue of this vector and the eigenvalue of this vector correspond to the columns of the diagonalized matrix. So that's what diagonalization essentially is. All right, we've got 2 more questions. We will be going over time, but I think I'll try to get through this quite quickly, and then we'll finish up. So this question, we've finished with the theory. We'll just go on to the question. So we're given a matrix A, and it has vectors v1 and v2 as eigenvectors with eigenvalues that sum to 0. So if we say that this has some eigenvalue lambda 1, and this has some eigenvalue lambda 2, well then lambda 1 plus lambda 2 has to equal 0. Find the positive one of these eigenvalues. Well, I mean, I could find this in a fairly straightforward way. I could do A times V1. A times V1 is going to be equal to it's going to be lambda 1 times V1. That's just straight from the definition of what a eigenvalue or eigenvector is. So I know what A is, so I'd have to do this multiplication here. 1, 0, 1, minus 10, minus 4, minus 8. Sorry, let's just write that a bit nicer because it's messy. Okay, and then V1, this would be minus 1, 0, 1. So this would be minus 1 times this. So this is going to be, I'll just rewrite it. I'll write it this way. Plus 5 minus 2, 0, 2. Okay. And this is equal to lambda 1 times V1. And V1 was just minus 1, 0, 1. Well, evidently, lambda 1 has to equal 2. So lambda 1 is equal to 2. Interestingly enough, because of this other condition that they gave us for the 2 eigenvalues have to sum to 0, lambda 2 has to equal minus 2 for this to be true. But you know, okay, we got lucky. The vector that we multiplied by A did give us a positive value. So the positive value for the eigenvalue was actually, it was a pretty good guess. This would be 2. but even if I got the other one, if I tried dotting v2 instead, well, then I would get -2, and then I'd know, oh, okay, well then the other solution, the positive one, should be 2, because they have to add to 0. All right, then I have to find the third eigenvalue, lambda3. So there's actually 3 eigenvalues here, which is interesting. This is not, they gave us 2 of them, but there are 3. And there are also, there are eigenvectors for that third eigenvalue. So how do we find the eigenvalue of lambda 3? Well, using some of the information that I said earlier, the trace of A is equal to the sum of eigenvalues. Which is equal to lambda 1 plus lambda 2 plus lambda 3. We know this is equal to 0, so that's equal to 3, lambda 3, and lambda 3 is just going to be the sum of these, which is -1. Okay, so that was part 1. Part 2, hence or otherwise, find a matrix P that will diagonalize A. Okay, so we need to find, if we want to find P, we need to find, well, the vectors that will have, we know all of these vectors are of multiplicity 1, right? So we would have 3 columns for this matrix P, and each of those would be corresponding to each of the eigenvalues. Now we have the the eigenvector for lambda 1 was -1, 0, 1. The eigenvalue for lambda 2 was -2, 1, 4. Now for lambda 3, well, we don't know actually what this is. So we have to find that. How do we find that? Well, we know that A of x is equal to -1, because it's lambda 3 of x. So this is going to be A plus I of x is equal to 0. So we just need to find the kernel of this. So the kernel of A plus I is equal, will give us the this vector, and it will be one vector in there. I might just skip over computing it, but what I can say is that the matrix P that will diagonalize A, so P, will be, well, if I take these vectors that I had before, so it'll be -1, 0, 1, -2, 1, 4, and then this last one, I mean, it's not very mathematically correct, but if I call the kernel of A plus I is equal to V3, well, then it would be equal to V3. Or V1, this would just be the vector V3 in that column. Not very correct syntax, but I think you get the point. Okay. All right, and then we'll do the last question. And I might just I'll just solve this one to completion, and then we'll wrap it up there. All right, so this one says, we're given matrix A, find the eigenvalues of A, and the algebraic and geometric multiplicities is A diagonalizable. Well, we know the condition for A is only when the multiplicities are equal. So this will follow once we do the first part. So we have A. What we can do is that we can rewrite the form in order to solve for the eigenvalues and eigenvectors as A minus lambda I times V is equal to 0. Now, this is equal to 1 minus lambda, 0, 0. This is going to be 0, 1 minus lambda, 0, 1 minus 1, 2 minus lambda. and we want to find the kernel. We want to find the first of all we'll find the eigenvalues. So we do the determinant of this. Now we can expand any which way we want. We can expand this way, this way. I think this way would be the nicest, and the reason for that is that we've only got one value here. The other two is 0, so they'll sort of disappear. So if I find the determinant of this, this is going to be equal to 1 minus lambda, so I'm expanding this way, and then it would be the determinant of 1 minus lambda, 0, minus 1, 2 minus lambda. And this is equal to 1 minus lambda, 1 minus lambda times 2 minus lambda minus 1 times 0, which is 0. And this is equal to 0. Okay. So we've got lambda is equal to 1 and lambda is equal to 2. This is a multiplicity 2 because we've got, well, I could combine these two into a power of 2. And this has multiplicity of 1. Right. Now, so we've got the algebraic multiplicities. Now we have to find the geometric ones. Now, in order to do that, we'll sub in these values for alpha, or for lambda, my bad. So let's just say for lambda 1, what we do is that we do a minus, what was lambda 1? Lambda 1 was 1 times I is equal to, well, that actually gets rid of a lot of the columns, which is, gets rid of 2 of the rows, which is nice. 1 minus 1, and this would be 1. Okay, and so if we want to find the kernel of this, of 0, 0, 0, 0, 0, 0, 1 minus 1 and 1, that's going to be, well, you can see that these are linear, there's no leading column. If I just rewrite this in a nicer way. So what this tells us is that x1, or there'll be 2 free variables here. So this would actually have 2 vectors that are part of this basis. So you would have x1 is equal to x2 minus x3. And so from this x1, x2, x3, did I use, I didn't actually state if I used that one, so that'll be fine. I'll just use this x2 minus x3, and I'll split them up the way I have before. So this one's going to be x2, 1, 1, 0, plus x3, minus 1, 0, 1. Yep. So these are our 2 vectors. Now these have a dimension of 2. Dimension of this is equal to 2, which is good because that means the geometric multiplicity of this is 2, which is the same as the algebraic multiplicity. So we're good so far. First part is working out pretty nicely. Now the second part, we need to find that for lambda is equal to 2, that the geometric multiplicity is 1. So if we want to find that, then we need to do a minus 2i. What is this? A minus 2i is going to be minus 1, 0, 0. Yep. And then it would be 1 minus 1, 0. Is that right? Yep. Okay. And then we need to find the kernel of this. You can already tell that a lot of this is tedious. But the big thing is that you don't get lost in the algebra. 1 minus 1, 0. Okay, so the kernel of this is going to be, well, if I rewrite this, I'll do 1 minus 1, 0. I'll flip those two. And then I would have, this is going to be minus 1, and then 0, 0, and then this would be 0 minus 1, 0. So I'm just reorganizing these so that it will look like row echelon form. 1 minus 1, 0. If I add that to that, it would be 0 minus 1, 0. And then if I add this to that, oh, actually, and then if I add this to that, sorry, it will be, is that right? Hold on 1 second. Should be, I think I might have done a mistake here. So this is going to be like that, and then minus 1 goes there, and then this goes here. The kernel of this should be 1 minus 1, 0. Add this to that, this would be 0 minus 1, 0. And then this would be, no, that is actually correct. Zero minus 1, 0, 0, 0, 0. Therefore, if we do x2 is equal, well, x2 has got to be equal to 0, and then x1 has to be equal to 0, and then x3 is free. So I was right. I was doubting myself for some reason. So this would be x1, x2, x3. This is going to be x3 times 0, 0, 1. You guys kind of see how I did that? I just sort of put that in the form, and I took out the x3. But the big thing is that this this basis has a dimension of 1. And this perfectly lines up with our algebraic multiplicity of 1. So it's diagonalizable. Diagonalizable. Okay. So that's that. Is asked, is it diagonalizable? The answer is yes, because the condition is satisfied. Now the last part. Hence or otherwise, find the eigenvalue of mu, of the inverse of A, and a to the power of 3 minus I, corresponding to some eigenvector B of A. Now, if you looked at this, you might be like inclined to sigh and cry because you think that, oh, I'll have to invert this matrix, and then I have to take this matrix to the power of 3, and then minus it, and then minus the identity from that, and then do this process in order to find some eigenvalue. That is one way to do it, but it is terribly, terribly inefficient. There is a pretty neat observation you can do from the definition that allows you to get a general solution for the eigenvalues of some sort of manipulation of A. It could be like a polynomial of A, and you can actually get a solution of mu in terms of the lambdas that we found before. So I can do that for you right now. We know from definition that x is equal to mu x. We need to find some mu. Actually, no, we won't work the other way around. We'll start from what we already know. We know that this is true from definition. We'll use from lambda. This is in regards to this first part. So if I want to find a squared, I could do a times a. I can left multiply this by a to a lambda x. This is going to be a equal to a squared x is equal to, I can take out the lambda because of our properties, and this is just this. So this is actually equal to lambda times lambda x is equal to lambda squared of x. So that's how you find it if you've got a squared. Now we want a cubed. You can imagine to do this again, you just multiply by a again, and then you take out the a, or you take out the lambdas from that, and then that turns into another lambda. I can do that quickly. So it'd be a cubed x is equal to, it would be a times lambda squared v, which is equal to lambda squared times a, sorry, it's not v, x of x, which is equal to lambda squared times lambda times x, which is equal to lambda cubed of x. So that's a cubed. Now we don't want a cubed, we want a cubed minus I. So if we want to find a cubed minus I, well, we can do a cubed minus I, which is x, is equal to a cubed of x minus x, which is equal to, this is going to be, oh, actually, hold on one second. This will be, because we know that ax is equal to lambda to 1, so that is going to be lambda cubed of x minus x, which is going to be lambda cubed minus 1. So this is going to be our mu. Does that make sense? Sort of got lost in the algebra there, but yeah. So our mu is going to be equal to this for that second part actually. If I want to do the first part, it's a bit different, but a lot of the same method is going to be used. So this is going to be equal to this, where is that, x? If I multiply both sides by a inverse to a inverse of lambda x, this is going to be x because this is the identity, I. This is going to be equal to lambda times this. So a inverse of x is going to equal to 1 on lambda x. Now there is a caveat, lambda can't equal 0, but you don't usually when we do eigenvalues, lambda isn't equal to 0 because that'd be it's like a degenerate solution. So you don't really consider that. But what you would have is that this is equal to this. So mu could be 1 on lambda. And that would solve for this one, and this one would solve for that one. And that's the general solution for some b. They called it b here. I probably should have called these b. But you get the gist. Okay, that's all. Was there anything I wanted to go through as well? No, I don't think so. I think that's pretty much it. Does anyone have any questions about any of the content before we wrap up? You guys have been very patient with us. We're 20 minutes over time. If not, yeah, I guess we'll just wrap it up here. Thank you. All right, let's have a look.